So if you have any group G, any group, and you have an element G in G, there's a natural subgroup that I'll denote by H, which I'll write like this, which is sometimes called the cyclic subgroup generated by Z, which consists of all products of G with itself. It's the smallest subgroup that could contain this element. So it consists of things like E, G. Since it has G in it, it has to have G inverse in it. Then it has to have G squared in it. Then it has to have G to the minus 2. So it consists of all powers of G. Where the 0th power is defined to be the identity. Because if you have the element G in it, you certainly have to have all powers of G in it, if it's closed under multiplication and inversion. Moreover, once you get all powers of G in it, then that's certainly closed under multiplication. You multiply 2 powers of G, you get another. I mean, the power law works in a group just like it does in normal arithmetic. Because this just means the product of G with itself m times, and this means the product of G with itself n times. So when you take the whole product, you have the product of G with itself m plus n times. The inverse of G to the m is G to the minus m. And that's contained in here. So this is certainly closed under addition and inversion and contains the identity element. So there it is. There's the cyclic subgroup. However, and it's a big caveat, don't necessarily think that those powers are distinct. And there could be a point where you take the power and you get back to the identity element. We saw that in the symmetric group. In S3, we had this element tau with the property that tau squared was the identity element. So if we took the cyclic subgroup generated by tau in S3, it would just be the group E tau. It would be that subgroup of order 2. So that's a big question. Namely, do you get to a power of G where it becomes the identity element or not? So if G to the m is equal to the identity, and m is the smallest power, we say m is the order of G in G. And if no power, G to the m equals the identity, smallest positive such power, for m greater than 0, we say G has infinite order. So the elements in Z all have infinite order. Once you get to an element which is, except for 0, which has order 1. Once you get to a positive integer, no matter how many times you add it to itself, you never get back to the identity because you keep marching out. But in the symmetric group, on 3 letters, we find that this tau has order 2. Someone has a phone call. And then we find that sigma, if you cube it, you get to the identity, has order 3. Does that signify the class is over?